Okay, welcome back. Now we're going to prove some properties of the formal group. And one property that is important is the following. So for each n bigger or equal to 1, the map that is going from the formal group for the m to the nth power of the maximal ideal modulo the formal group for the n plus 1th power of the maximal ideal that goes to the corresponding map just on powers of the maximal ideal, that this is induced by the identity map on sets is an isomorphism of groups. So this is meant to give you an idea of what's happening at the level of of the formal group, what kind of a structure is there as you raise powers of the maximal ideal. So the map here is just going from, remember that the formal group, the set, the underlying set is still, it's still just the maximal ideal, or in this case, the nth power of the maximal ideal, that's the underlying set, right? So I can actually send just the element z to the element z on the other side, and that will give me a map. And this is saying that this is actually an isomorphism of groups. Okay, and then B, let P be the characteristic of the residue field. The residue field might be of characteristic 0, okay, in some cases. So in any case, P equals 0 is possible here. But as I said at the end of the previous video, we are going to be interested in knowing what is the torsion, what torsion elements are there in a formal group over QP, for example. So this is going to say that then every torsion element of the formal group has order a power of P. Okay, so here's the proof of these two facts. So for part A, as I said, the underlying sets are the same. So underlying sets of elements are the same. So it suffices to prove that this is a form. That the map is a hom. But when I do addition on the formal group, the addition on the formal group is just given by the power series evaluated at x and y. Okay, and the power series starts as x plus y plus hot, right, by elements of higher order terms. And if x and y, so if x and y now are in the nth power of the maximal ideal, then the higher order terms are going to be at least a square, so they're going to be at least in the 2nth power of the maximal ideal. So this is just congruent to x plus y modulo m to the 2n. Okay, and if n is at least 1, that is at least m squared. So yeah, so this is modulo m to the n plus 1. That is just x plus y. Okay, so so this is just saying then that x plus y. How do you say it? Yeah, actually, if we give this a map a name, this is just saying that psi of x plus y is x plus y, or x plus y modulo m to the n plus 1. Okay, so it is a HOM, and then it's easy to see that that is also an isomorphism because the sets are the same. Okay, okay, great. And then for the second part, the fact that every torsion element has a power of p, it suffices to show that there are no elements of order prime to p. There are no elements of order, let's call it m, that is prime to p. Okay, so we assume that the GCD of m and p is 1, and suppose for a contradiction that x is in here in the m torsion of the formal group, so that m times x is 0. Okay, but since m and p are relatively prime, that tells me that m itself cannot be in the maximal ideal. Okay, here we're assuming the characteristic is p, so they cannot be. It cannot be in the maximal ideal, and then we've seen that the multiplication by m map in the formal group is an isomorphism. But then that implies that is at the level of formal groups, but this induces that M is actually an isomorphism at the level of the groups attached to the formal group. And therefore, the kernel is 0. It's trivial. And that tells me that X itself was the 0 element. And therefore, there was no element of order M prime to P. And I'm done. This will be very important to analyze the torsion of elliptic curves. This, by the way, if you remember again from the exact sequence we talked about, it's telling you what is happening in terms of torsion here. Okay, there is still some torsion that can come from here. So there may still be some p power torsion here, what it's or prime to p torsion here, but it's not coming from here. So we are sort of like analyzing chunks of this exact sequence one at a time, and then see where the points of finite order would be. All right. So now let me talk about the invariant differential.
Alvaro, could we go back real quick? Sorry.
Yeah.
Just a really minor question. Can you go over again, why is it that M being relatively prime to P means that M is not in the maximal ideal? Can you explain that implication? I think I missed something.
Well, how do you prove that? So in general, well, I mean, first of all, in the in the case, our toy case, right? We know that the maximal ideal. So if R is ZP, then the maximal ideal is PZP.
Yeah.
Right. In the general case, if the characteristic is P, what that means is that R modulo M is little k of characteristic P. And therefore, if you look at the map that sends R to R mod M, then the things that vanish are the things that are in the maximal ideal. But if you take an M that is relatively prime to P, and then you send it here and consider it here, M modulo the maximal ideal, then M is not zero in little k, because M is not divisible by P.
Okay.
Okay, and so now you think of little k is FP or an extension of FP. An integer that is not divisible by P is one of the classes in the base field FP which are non-zero.
Okay.
So it's non-zero there, so it cannot be in the kernel, so it cannot be in the maximal ideal.
All right, that makes sense now. Thank you so much.
Yep. All right. So now what we're going to do is define the invariant differential. So we have, again, a formal group. Over R. We did have the invariant differential for the group, for the formal group of an elliptic curve. I just took the invariant differential that we knew from an elliptic curve and said, well, this is a differential. But in general, an invariant differential on the formal group is a differential form. So essentially a symbol, which is just a power series times the symbol dt. So it is a power series times dt. Okay, it lives there, such that the property is that it's differential, or that it's invariant under the invariant part of invariant differential is that it's invariant under translation. How do I translate a number t in a formal group? Add a number s to it. How do I add s? Through the capital F, through my power series. So the property that it needs to satisfy is that the invariant differential evaluated at FTS has to be the same that the differential is still at t. So this is what it means to be invariant. And which actually, in terms of the power series, what this means is that P of FTS ddx of FTS, that has to be the same that T, that P of T. All right. So, and we say that the differential is normalized if P of 0 is 1. Okay, so for example, the invariant differential for GA, so where F, remember, is just addition, then the invariant differential here is just dt. So the power series is just the number 1. For multiplicative formal group, which remember is x plus y plus xy, the invariant differential is actually 1 over 1 plus t dt. Okay, which is the power series. By that is a nickname for the power series 1 minus t plus t squared minus dt. Okay. And I'm not going to, there's a lot more about invariant differentials in the book, but all I need is that from the theory of the invariant differential, it will come back in a moment, the invariant differential, but something that you prove using invariant differentials, and then there is no mention of the invariant differential in the statement, but it is proved using that, is the following. Have I run out of pages? Looks like I'm writing a lot today. Let me add some more pages here. What time is it? Oh, yeah. Okay. So something that you prove using the invariant differential is the following corollary. I believe is 4.4 in the book, which is the following. So let F be a formal group and P be a prime. Then there exist a power series f of t and g of t in power series in R with f of 0 equals g of 0 equals 0, such that multiplication by p is actually p times f of t plus a power series g evaluated at t to the p. Okay, I'm not going to prove that, but that gives you a very interesting decomposition of the multiplication by p map. It tells you that either there are coefficients, there's 2 groups of monomials in the expansion, all those that have p, that the coefficient is divisible by p, or they are not divisible by p, but then they are powers of p. The exponent is a multiple of p in those monomials. Okay, so for example, you can see this in real life, that if you have an elliptic curve and you look at the formal group of an elliptic curve, let's look at what is multiplication by 3. Multiplication by 3, it turns out you can write it as 3 times, so monomials that are divisible by 3, there is t, and has to start with 3t, and then minus a1 t squared plus 4a1 a2 minus 13 a3 t to the 4 plus dot, plus, and then there are other terms that are the ones that have the t cube, that have t6, t9, and so on, the ones that are that have a t cube to some power as the power of t. So for example, it starts with a1 squared minus 8a2 t cube plus something in t6 plus so on. Okay, and you can extract that information and actually write what the f and the g are for these for this multiplication by 3 map. Okay, I have like 3 minutes, but let me just say, yeah, what is actually the formal logarithm. So something else that we're going to need are the formal logarithm of the formal exponential for a formal group. So suppose R is of characteristic 0 now, and let K be the ring of functions. So for example, I'll just put it as R tensor Q, and of F over R formal group. Then let the invariant differential be omega t. Let normalized or invariant differential, I'm going to write it as 1 plus c1t plus c2t squared plus dt. Then the formal logarithm, of the formal group is, we write log f, that's an ugly f, too calligraphic, log f of t is the formal integral of the differential. That's what differentials are for, to integrate them, which is t plus c1 over 2 t squared plus c2 over 3t cubed, etc., which is in k, now power series in k. The invariant differential is defined over R. When you integrate, you introduce the denominator, so this is going to be in k. Okay? But notice that this power series starts with a 1 plus ... Remember that there was a lemma that we proved in the previous video, I guess, that said that if your power series starts with a times t plus other things, and that a is a unit, 1 is a unit, then there is a unique inverse power series. That unique inverse power series is the formal exponential. So the formal exponential of a formal group is the unique power series exp of t in k of t, in power series in t, such that the log of the formal log composed with the formal exponential is the same that the formal exponential, whoops, I lost my f, composed with the formal logarithm gives you the identity. Okay, and why are these things called formal logarithm and exponential? Well, those names come from the fact that if you look at the multiplicative formal group over GM, the invariant differential is 1 over 1 plus t dt. So the invariant or the formal logarithm is going to be the formal integral of 1 over 1 plus t dt, which is the sum of minus 1 to the n t to the n over n, which is the expansion of the logarithm. Okay, and then the formal exponential is going to be the power series that does that job of being the inverse of the power series for log, which is the power series of e to the t minus 1. So that's where the log and exponential names come from. And remember that, so the exponential gives you a hom between what? So between the reals and the positive reals. So, or it gives you a map, a bijection between the two, and we're going to use the logarithms and the exponentials to come up with some isomorphisms of formal groups. In particular, we're going to use the logarithm to do an isomorphism between a formal group and the formal additive group, so that we have an easier way of computing things about formal groups in general. All right, so I'm going to stop there, and we'll continue next time with more stuff about formal groups.